Look at a single line of code or a single method, and the boundaries are clear. But as you zoom out, from method to class, to module, to library, to full application, the surface area expands. Designing the system that sits above all of these individual applications requires managing a massive, interconnected scale with no obvious starting point. At this altitude, the technical blueprints disappear. Instead, requirements usually arrive from business clients who understand the problem they want to solve, but not the technical solution. They deliver feature requests wrapped in high ambiguity. When faced with this ambiguity, the standard developer instinct is to build the features now and refactor the architecture later. At the system scale, that instinct fails. You cannot simply refactor a foundation that supports months of engineering time, heavy infrastructure costs, and strict service contracts. Getting the core architecture wrong from the start is prohibitively expensive. The architecture of a system is not driven by what the system does. It is dictated by how well it must execute those tasks and the hard operational boundaries it must survive within. Treating system design as a simple checklist of features leaves the foundation to chance, often resulting in a structure that cannot support the weight of the actual requirements. To move past a blank architectural canvas, you have to take that raw, ambiguous list of requirements and filter them into 3 distinct dimensions of drivers. The first dimension consists of features. These are the functional requirements that capture what the system is supposed to do. Features do not drive your architecture. You can force almost any arbitrary system design to execute a specific functional feature. The second dimension holds your quality attributes. These are the non-functional metrics that measure performance, scalability, and security. These are the pressures that actively shape your system structure. The third dimension comprises system constraints. These are the unnegotiable technical or regulatory limits imposed upon you, and they tightly bind your available solution space. Systems are rarely rewritten because a minor feature is missing. They fail under load because the architect prioritized basic functions over strict quality attributes and immutable system constraints. This diagram represents our primary engineering sandbox, a real-time streaming conversational AI platform. It illustrates a single conversational loop flowing from audio ingestion through voice activity detection, speech-to-text, LLM inference, text-to-speech, and finally egress. When defining a quality attribute for this pipeline, the first rule is testability. Here, the absolute headline metric is a total conversational loop of 800 milliseconds or less. Vague adjectives like demanding the system respond quickly are useless to an engineer. Architects must rely on strict, measurable numeric thresholds to make structural decisions. The second rule is trade-offs. No architecture can maximize all metrics simultaneously. For example, optimizing for extreme security, like deep packet encryption and multi-factor handshakes, naturally degrades raw performance, pushing processing time past our latency ceiling. The third rule is feasibility. Demanding cross-continent network latency under 100 milliseconds violates the speed of light in fiber networks. Requirements must be bounded by physical reality. Returning to our exact parameters, we apply the strict 800 millisecond conversational loop metric back over our pipeline. Normally, developers lean on standard, stateless REST components as a default design solution for moving data. However, a sub-800 millisecond response time leaves no room for the overhead of standard stateless REST architecture. Every millisecond spent opening and closing connections is time taken away from the actual inference and generation layers. To survive that latency requirement, the design is forced into continuous, stateful streaming using persistent WebSockets. A single, rigorously defined quality attribute dictated the shift to stateful streaming, overriding developer preference with the hard reality of the latency budget. While functional features do not determine the physical shape of the system, they serve a precise purpose. They define your operational boundaries. Instead of relying on a feature list from a client, architects use a 3-step functional discovery process to extract those boundaries. Step 1 requires identifying and enumerating every external person or system that interacts with your platform. Step 2 isolates specific, meaningful interaction models. You must separate the workflows of a successful transaction from the pathways of failure states. Step 3 expands these models onto a linear timeline. This UML sequence diagram maps the exact back-and-forth protocol handshake between an external client and the infrastructure gateway. This reveals a crucial architectural mechanism. Sequence diagrams act as your primary API discovery tools. The moment a specific action crosses the vertical line representing the system edge, it ceases to be an abstract idea. Every distinct message that crosses into the system boundary explicitly becomes a hard, public API contract. Applied to our AI sandbox, the moment a client WebSocket interaction attempts to push data across the gateway, it mandates a strict binary audio ingestion contract, codified into specific gRPC specifications. Public API endpoints should never be guessed or drafted arbitrarily in isolation. They are the technical manifestation of the system boundaries you identified in your use cases. Beyond latency and API boundaries, architects must manage unnegotiable external elements, such as reliance on third-party downstream AI providers. If a foundational, load-bearing pillar of your application suddenly fractures without warning, an entirely monolithic structure will fail completely. Downstream model vendors act as system constraints. These are technical realities and business decisions that have already been made for the architect. Relying tightly on these external vendors introduces fragility. If an AI provider introduces sudden token rate limits or drops a connection standard, a direct integration ensures that failure propagates. When the vendor node goes down, the tight coupling creates a catastrophic blast radius, immediately breaking the central conversational state machine. The specific defensive countermeasure against this constraint is loose coupling. By placing vendors behind an abstract service boundary within a gateway or orchestrator, you change the operational logic of the system. This service boundary acts as a firewall. It ensures the core conversational state machine remains protected and operational during an external outage. You gain the ability to drop a failed connection and swap in a secondary third-party vendor without needing to rewrite your core platform code. System constraints are not merely passive limitations you document on a wiki. They are structural hazards that must be actively quarantined. This is the fully assembled architecture for the real-time streaming conversational AI platform. The stateful streaming pipelines were forced into existence by the strict latency quality attribute. The public API layer was defined by mapping the exact boundaries of our sequence diagrams, and the orchestrator layer was built to contain the system constraints of external vendors. A robust system architecture is not a collection of best guesses. It is the calculated result of meeting specific performance metrics within strict operational boundaries.